Good morning. How are y'all doing?
Good.
Yeah?
Woo! Yeah. Yeah.
God. Yeah. For the rest of the camp, anytime I talk to you, it's very important that we begin with a huge round of applause for me. That was awesome. Thank you. That made my morning. What's that? Yes. What's your name? You don't kiss my butt. That's not a cool way to start things. All right, I'm shipwrecked up here because everybody's trying to trap me with cords. My name is Scott Herndon. I'm the Associate Director of Debate at the University of Texas at Dallas. That probably doesn't mean anything to you. I will tell you what's cool is your topic. I am totally jealous of the high school topic. Do you have a question?
Can I move?
Can you move? Yeah, absolutely. I am totally jealous of your topic. I debated on a space topic back in 1990, when I was very young, a long time ago. Interestingly enough, not a ton of stuff has changed. The time frame debates we're having on those disads, fairly true. We got 20 to 30 years before we get to a lot of this stuff. But I will say I think your topic's pretty sick. We're going to talk today a little bit about one of the larger areas, like aft areas in the topic, one of the larger areas of debates, one of the most important reasons that we think about going to space, which is energy. Energy consumption is a huge problem on Earth. Fossil fuels are running out, right? Peak oil is happening. A lot of other resources on Earth that we might use for energy are also depleting or becoming extremely rare, difficult to get to. Lots of times people who are not friendly to the United States have access to these things and we don't. And so moving to space is one of the great ways for the United States to sort of exert itself both in that realm and also have access to energy. There's lots and lots of energy. We're going to talk about three particular sets of things today. We're going to talk about some of the mining kind of areas and what we might do to mine in space. Talk a little bit about solar-powered satellites and some nuclear propulsion and other stuff. Some things you should know. If I talk too fast, that's totally my bad, but you should raise your hand and say something to me, like ask questions. You don't have to wait to the end of the lecture to ask questions. If you do that, sometimes you forget, sometimes I forget, and then we don't answer questions. So if you got questions, or if I'm not explaining something, or if I can give you some more detail, by all means let me know, all right? So I'm going to get started by first talking about some of the areas of mining. Mining's pretty cool in space. Two primary things, or the two kind of primary energy-related areas where we'll talk a lot about mining are the moon, lunar mining. One of the specific things there is Helium-3, or HE3 as it is often abbreviated, and also the process of mining asteroids. We'll talk a little bit about that. Although, we're kind of cheating, because asteroid mining isn't necessarily all about energy and propulsion, but it's still pretty cool, and there are things that we mine from those asteroids that are related to energy. So the first thing I want to talk about is the moon and HE3. I bet all of you have had some sort of debate where you've used the starter pack and the HE3 file, so you kind of got some idea of kind of what Helium-3 is and where it comes from. I'll give you a hint. It comes from the moon, pictured here. This is the moon. That stuff around the top of the moon, well, you can't really see it all that carefully, but the soily area of the moon here, the loose kind of silt and dust that's there is called the moon's regolith, and that is where Helium-3 collects. I'll tell you a little bit about Helium-3. First of all, it's a product of solar winds. The space itself, vacuum space, is filled with a whole bunch of different kinds of gases, and one of the primary gases that's filled with is something called Helium-3. We're used to Helium-4. You know, when you put it in your balloon floats away and your voice gets squeaky, that's terrestrial Helium-4, pretty abundant on Earth. Unfortunately for us, it's a little bit harder to get to the Helium-3, which we have a whole lot of purposes for its use. I'll get to that in a second. So solar winds. This sun itself, basically the heat of the sun, the solar winds, those push the gases throughout space, and they collect in loose soils all over the place. Since the atmosphere of the moon is fairly slight, not a lot of atmosphere on the moon, can't take your helmet off and breathe there, and there's a lot of very loose silt soil on the regolith, R-E-G-O-L-I-T-H, regolith of the moon. It's not soil like we think of, like you're not going to grow corn in it, but it's like where the dust and such is. It collects there fairly easily and sort of stays there. We think there are tons, billions of tons of Helium-3 on the moon. Now, during the formation of the Earth as well, Helium-3 was fairly abundant. Solar winds, again, deposited on Earth as Earth's atmosphere was forming. The problem for humans is that it's not very common to get to it. It's deep within the mantle of Earth. So mining for Helium-3 on the Earth is not a very practical solution. It's difficult to get at, unfortunately for us. But it can be got at on the moon. Like I said, the product of solar winds. It also happens on Earth that it's a byproduct, the creation of Helium-3, the isotope, is a byproduct of nuclear weapons deterioration. So all those nuclear weapons that we have in silos all over the place in Texas and Kansas, Nebraska, et cetera, all the weapons that we store have an element in them called tritium. Tritium is part of what we use to make the fusion reaction, right, to blow up the weapon. And as it degrades over time, it releases helium-3. So most of the terrestrial stores of helium-3 come from the degradation of this tritium element, which is in nuclear weapons. Now, as you can imagine, over the process of our entire nuclear program, we've not produced a ton of this. It's a byproduct of degradation, as I said, and so there's not a lot of it that's produced. In fact, about 150 pounds of it produced total in the history of our nuclear weapons program. Also not super easy to refine that way. That's just the U.S. nuclear weapons program. Obviously, Russia and China's weapons produce a little bit more, so that number would skew a little higher globally. But you get the idea. It's not particularly easy for us to get at. As I said, it's a rare earth element, but abundant on the moon's regolith or soil. So that's the reason why we would go to the moon, you see, to get the helium-3. Good thing about helium-3 is that we believe it's a potentially limitless energy source. We know that combined, and I'll show you how it's combined here in just a second, we'll watch some cool videos about that. We know that when it's combined with an element like deuterium, that it can create a whole lot of energy. So if there is as much helium-3 on the moon as we hope and or think there is, there's probably enough to power basically all energy on the planet for a good long time. The estimate is something like 300 years or so. So many, many generations of humans could be powering their cities and other things based on the energy that we create from helium-3 if we can get it off the moon, which is sort of the trick, right? Another upside to helium-3, as it creates, if I haven't, I guess I didn't say this directly yet, we'll watch a video that says this, but the process of this is nuclear fusion, right? Fission is what we're used to for nuclear weapons. We create energy through fission as well. We break the atoms apart. That releases a bunch of energy when they're broken apart. Now, nuclear fusion is the opposite. You superheat the atoms together, and then the process of them merging creates energy. Now, when we usually nuclear fusion, what happens? What's one of the byproducts? What happened in Japan, say, when all that stuff melted down? It gets too hot, right? And it releases radioactivity. Highly, highly radioactive, which makes it fairly dangerous. And also not particularly appealing as a long-term, going forward energy option. It's not as clean, say, as as fission would be, or solar, or other sorts of renewable energy. So the upside is that helium-3, when combined with deuterium, does not have the same radioactive energy release. It releases a huge magnitude of energy, but without all the radioactivity. That's if you do it with an H3 deuterium connection, right? There's another way to do it with the two helium molecules put together, and that might even have less of a radioactive output. So on the upside, not a lot of radioactivity produced by energy created with helium-3, and that would be pretty awesome for people on Earth. It means that there's less reactor meltdown and stuff like that. It begs the question, of course, whether or not that's currently feasible, and we'll talk about the feasibility of that in just a moment. So no radioactive output. These are some of the upsides of helium-3. This is Mr. Helium-3. If you see Mr. Helium-3 out in the street, you would say hi, and now that you have a picture of Mr. or Mrs. Helium-3, you know what you're looking for. I really don't know why I included that necessarily, but I thought it was pretty cool to look at this stuff. I'm going to show a short video here that sort of describes the process of the way we use helium, deuterium, and tritium now to create energy. And it's about 7 minutes long, and it's pretty cool. It's a little slow, but there's a lot of good information. And I think we'll all get some of that. It kind of starts right in the middle here talking about moon rocks.
Yet recent studies of these rocks suggest they contain something so important it could dwarf even their black market value. Since the 1970s, scientists from across Europe have been beating a track to the Oxfordshire village of Culham. Here, they are pursuing a new form of power that could transform life on Earth. It's called nuclear fusion, an attempt to reproduce on Earth the reaction that fuels the sun.
Experiments going on behind me are in a machine called JET, which is about the size of a house, but it only has 1/100th of a gram of fuel in it at any one time. If you turn that into a power station, it would need about 1 kilogram of fuel during a day, compared to a fossil fuel station, which would need about 10,000 tons of fuel to produce the same energy.
The reaction is fueled by hydrogen, the commonest element on Earth. It's based on the principle that if instead of splitting atoms, as in conventional nuclear power, you heat them up to millions of degrees centigrade, they fuse, releasing huge amounts of energy.
The process requires us to reach very high temperatures. It's what powers the sun and all the stars. So if these were two hydrogen atoms, if they just move together slowly, they bounce off each other. It's only by getting them to very high temperatures they can come close enough to capture each other.
Could you slow the countdown, please?
But as scientists experiment with the technology, they've hit a major problem. This experimental reaction produces enough power to supply the energy needs of a small town. But it also produces enormous quantities of highly destructive neutrons. If the experiment is run for longer than a few seconds, it begins to destroy the walls of the reactor.
Of the power comes out in an energetic particle called a neutron, which flies into the wall, the first wall of the reactor chamber, and striking it can damage the material. So we just have to accept that we change the wall perhaps every 5 years, something like that.
It's one of the main obstacles to using fusion as a reliable, long-term source of energy. But there may be an answer. Since the 1980s, Jerry Kolchinsky has been nursing a dream. He believes there's a way of fueling a fusion reactor that is much less destructive. It's based on the idea of replacing hydrogen as a fuel with a gas called helium-3.
We actually are bringing in helium-3 through this tube, which is connected to a helium-3 cylinder.
Helium-3 is chemically very close to hydrogen. But Kolchinsky has found that the reaction produces far fewer destructive neutrons than conventional hydrogen fusion.
We have very few neutrons in the system, and we think a device like this could run for the lifetime of the reactor. That is a big difference compared to trying to run one where 80% of the energy comes out as neutrons.
But the only helium-3 on Earth comes from decommissioned nuclear weapons and is extremely scarce.
Many people have known about the helium-3 reaction for many, many years, but they would always end their lectures with, well, there's no helium-3 around, so therefore we don't have to worry about this fuel cycle, we'll go on to something else.
Then, Kolchinsky ran into an acquaintance. Harrison Schmitt was the only research scientist among the 12 Apollo astronauts.
This boulder is typical of the granitic rocks that form the core.
He's a trained geologist.
Probably an intrusive rock, although it's sometimes very difficult.
If I can't crack the corner and get that contact, it's obviously very cohesive and fragmental-like.
Schmitt came back from the moon and analyzed samples he'd collected. He found they contained significant quantities of helium-3.
We have significant information about the distribution of helium-3. We, of course, sampled the soils at Tranquility Base where Neil Armstrong landed. We have indications of high titanium, which is a surrogate for helium-3. And then also the polar regions have high concentrations there. So we have a pretty good basic understanding right now.